Hey everybody, this is section 3.9, variations of parameters. So this is a new method that we'll be talking about today on how to find a particular solution to the general second order linear differential equation of y double prime plus p sub t of y prime plus q of t of y is equal to g of t. So first of all, we're going to assume one thing here. We're going to assume that y1, y2 is a fundamental set of solutions of the homogeneous equation. So our complementary equation would look like y sub c is equal to c1, y1 plus c2, y2. Now I did leave off the parentheses y sub t, the t here to show that these are functions of t. And this is because later on we're going to be dealing with a lot of different variables going on. And so I left those off for simplicity's sake. All right, so this idea of the variation of parameters is actually kind of been introduced before when we talked about the reduction of order. And so here we're going to assume that our particular equation, y of p of t, is equal to u1, y1 plus u2, y2. Okay, where u1 and u2 are functions of t. Okay, so again, y is a function of t, u is a function of t. The c1, c2 here is just like normal. These are just constant coefficients in that case. All right, so the very first thing that we need to do is we need to find out, okay, well, what is the first and second derivative of our particular equation? So when we put it into here, we can solve for y1 and u1 and u2. All right, so our first derivative is simply, we have a nice product rule going on here. So first times the derivative of the second, so u1 y1 prime plus, second times the derivative of the first, u1 prime y1 plus, now the derivative of u2 y2. So u2 y2 prime plus u2 prime plus, or times y sub 2. All right, one thing that we are going to do to help with our calculations, and also something that we're looking ahead for, is we are going to set the constraint. So there's a couple of these. And one of our constraints that we're going to have, so the first one we're going to have, so there are going to be two, is that y1 u1 prime plus y2 u2 prime is equal to 0. All right, so what that means is these pieces here are going to go to 0, leaving us with u1 y1 prime plus u2 y2 prime. Okay, there's a reason we're going for that is because as we take the second derivative, we are going to get something more complicated if we did not have that constraint in there. All right. Now, based upon that, that makes this a little bit easier as well to find the second derivative. Okay, so our second derivative of the particular equation that we're assuming here. Okay, first times the derivative of the second, so we're going to get u1 y1 double prime plus u2 y2 double prime plus, so I went ahead and did those together, and then we're going to get u1 prime y1 prime plus u2 prime y2 prime. All right, so now that we have all of our pieces for our particular equation, we're going to plug it into our differential equation up there. All right, so adding this together, so you're going to get our y2 here, or y double prime. So we're going to get u1 y1 double prime plus u2 y2 double prime plus u1 prime y1 prime plus u2 prime plus y2 prime. This is why I said we're going to leave off these t's here. Plus now our piece of t times our y1 prime. All right, using our constraint here. So we're just going to have u1 y1 prime plus u2 y2 prime. All right, and then our q of t is going to be multiplying our original particular equation here. All right, so plus q of t of u1, y1 plus u2, y2. And this is all equal to g of t. All right, so let's go through here. There are some things that we can combine here to help us out. Remember what we said about these two solutions. They're solutions to the homogeneous equation, meaning if we could combine these to get this format using y1 and y2, if we could rewrite it, parts of those can go to 0 and we're eliminating that from our equation. And in fact, we could do that here. So notice u1, it's multiplied by y double prime here. And then we have u1 times y1 prime times p of t. So if I factored that out, I get p of t y1 prime and q of t u1 y1. Plus, okay, so we got that taken care of, that taken care of, that taken care of, so we're bookkeeping here. All right, now I'm going to do the same thing with, see if there's anything with the u2, and in fact there is. So it's multiplied by a y sub 2 double prime plus p of t y2 prime, that's this term here, plus q of t times y sub 2. All right, so I get sort of that term and that term, and look what's left. We have these two terms here, plus u1 prime y1 prime plus u2 prime y2 prime. And this is all equal to g of t. All right. Well, think about this. We just stated that these guys are solutions to the homogeneous equation, meaning this has got to be 0, and this term has to be 0, leaving us, in the end, just simply u1 prime times y1 prime plus u2 prime y2 prime, and that's supposed to equal g of t. This is our second constraint. We're actually going to be solving this here in just a second for u1 and y1. All right, so constraint 2 is that u1 prime y1 prime plus u2 prime y2 prime is equal to g of t. So that's our constraint right now. All right, so I'm going to erase here. So this is where our calculation is coming from. All right. So look at that. We have a system of linear equations actually with two unknowns. Because we already know, we're assuming that we know y1 and y2. Therefore, we would know their derivatives. Okay? So we have y1, u1, rewrite that. u1 prime y1 plus u2 prime y2 is equal to 0. That was our first constraint. And then we have u1 y1 both prime plus u2 prime y2 prime is equal to g of t. We can rewrite this as a system of linear equations, and then actually we're going to use matrices here in just a second. So rewriting this as in matrix format, we have y1, y2, y1 prime, y2 prime, times u1 1 prime and u2 prime. This is equal to the matrix 0 g of t. All right, so this is how our system looks in terms of a matrix. All right, first of all, we need to be able to solve for u1 prime, u2 prime. Well, what we could do is we can multiply both sides by the inverse of this first matrix, but we need to make sure, well, does this have an inverse? Well, a matrix A, so if you don't recall, so recall for a second, that a matrix A has an inverse, A inverse, if its determinant is not equal to 0. Okay? well, do we know anything about this? Well, yeah, we said that y1, y2 forms a fundamental set. Well, if they form a fundamental set, that means the Wronskian, the determinant of this 2 by 2 matrix, is not equal to 0. Okay? So, that means this does have an inverse. And in fact, here's how we're going to write it. So, first of all, I'm going to rewrite this. u1 prime, u2 prime is equal to, all right, when you do multiply by the inverse matrix, you also have to multiply by 1 over the determinant. So 1 over the Wronskian with respect to t, and again I'm just showing that here, times, and there is a thing that you have to do with the inverse. Here you're going to write this as u2 prime and negative y sub 2, negative y sub 1 prime, and y sub 1. Okay, so you've changed these corners here, and then you make these negative. Okay, so you're just changing the roles and then making these guys negative. That's where that's coming from. And then we're going to multiply this by 0 and g of t. All right, so based upon that, we're going to get the following matrix. Okay, so following matrix multiplication. So we have our scalar multiple out here that we're going to multiply each of these terms by. Then I'm going to multiply this term by this term, and then add this term times this term there. So if we have y2 prime times 0, we're going to get 0 out, plus negative y2 g of t, all divided by our Wronskian. And then the same thing here, we're going to multiply by this row to this column. So it's this term times this term plus this term times this term. Well, negative y prime here is going to be 0. And then we're going to get y prime g of, or sorry, y1 gt divided by our Wronskian. So another way that we can write that now is saying u1 prime is equal to negative y sub 2 g of t divided by w sub t, and u2 prime is equal to y1 g of t divided by our Wronskian. All right. Well, that doesn't really help us. That gives us a nice piece here, but we need u1, y1, because how we set up our particular equation. Again, just as a reminder, we stated that our particular equation is of the form u1, y1 plus u2, y2. Okay, so we need to figure out what those guys are. Well, this is a derivative. That means we just need to take the antiderivative of both sides. All right, so keeping that in mind, give ourselves a little bit more room. So u1 is equal to the integral of u1 prime dt, which is equal to the integral of negative y of 2 g of t divided by our Wronskian with respect to t. And u2 is equal to the integral of u2 prime dt, which is equal to the integral of y1 g of t divided by our Wronskian. All right. Now that we have integrated, or at least shown that we're integrating, that means our particular equation is going to look a little bit funky here just because of all the information that's going into it, but our particular equation is going to be u1, which is the integral, and actually we're going to rewrite this just a little bit. So u1, y1, so I'm going to have this y1 out in front, times the integral of u1, which is negative y2 g of t divided by our Wronskian, plus y2 times u2 u2, which is y1 g of t divided by our Wronskian. All right, and that is our particular solution. So, variation of parameters is very easy when we get there. Well, it's not very easy. It's just algebraically difficult, but we can get there. It's actually just pretty tedious is what happens. And so I could talk about it all day long, but seeing an example is probably the best thing out there. So with the next video, I'm going to show you how to go through one of these. All right, so we're back. So I wanted to find the general solution to the following differential equation. Y double prime minus 3y prime plus 2y is equal to 1 over 1 plus e to the negative t. All right, so the very first thing that we need to do in order to apply this variation of parameters is, one thing is I want to point out. Notice with our previous example, so notice this has got constant coefficients in there, so we could technically start thinking about section 3.8. However, we still have some issues. This does not fit any of our prescribed values in that table that we dealt with in 3.8. So what we're going to have to do is use variation of parameters in order to do this. This is why variation of parameters is so important. It's because it takes care of any of those situations where we can't use undetermined coefficients. All right, so with this one, we still need to find our complementary because that's going to give us the two solutions that we're going to use for the variation of parameters. So my first is find y sub c of t. Well, that's our first step. So I need to set up my characteristic equation. Lambda squared minus 3 lambda plus 2 is equal to 0. Again, setting this up for the homogeneous equation. All right. Well, factoring this, we get lambda minus 2 times lambda minus 1 is equal to 0. So lambda is either equal to positive 2 or positive 1. So that means our complementary equation is C1 e to the 2t plus C2 e to the t. All right, and these are going to be our y1 and y2. So y1 is going to be e to the 2t, and y2 is equal to e to the t. These are going to be the ones that we assume are form the fundamental set and use in our particular equation. Okay, so the very first thing that I need to do is double check that this forms a fundamental set. So I'm going to check the Wronskian on this one. All right, so I have e to the 2t, e to the t, and this is equal to the determinant of e to the 2t, e to the t. Nice thing is we just get e to the t's out of this one, and we get 2e to the 2t as the derivative. Okay, again, these are the y1, y2. These are the derivatives of that. All right, find the determinant is we multiply the diagonals and subtract. So we're going to get e to the 3t minus e to the, minus, don't leave off your constant values, minus the 2e to the 3t. And we get negative e to the 3t, which does not equal 0 for any value of t. So this does form a fundamental set, so we're ready to move on into our second part. Okay, so what we're going to do now is set up and find our particular equation. u1, y1 plus u2, y2. All right, in order to solve that, well, we know already through our setup, so this is the nice thing is we're going to be using that similar setup of having the 0 gt. So the way you can start this is not having to reinvent the wheel. So start back where we're dealing with the matrices. All right. So a better way to write this is we already know that we're looking for u1 prime, u2 prime. And we're going to equal that to 1 over our Wronskian, negative 3e to the t. Or sorry, negative e to the 3t times, all right, we change the positions of these two, so we switch diagonal, so we're going to get e to the t, e to the 2t here, And then we're going to make this diagonal negative. Okay, so we're going to get negative 2e to the 2t and negative e to the t. We're going to multiply this by 0 and g of t. And this will generate our equation. Or y, our u1 prime and our u2 prime. And in fact, since we already know our g of t, we're going to go ahead and plug that in. 1 plus e to the negative t on the bottom. And now we're ready to multiply. All right. So u1 prime is going to equal e to the t times 0, which is 0. So we're going to get negative e to the t multiplied by this. And then also multiplied by our Wronskian, our scalar multiplier. So therefore we're going to get, and in fact, let's make life a little bit easier. So we notice that we get 1 over negative e to the 3t. I'm going to rewrite that and make this negative e to the negative 3 of t. So the same thing, it's just going to make life a little bit more easier when we're dealing with our calculations. So when I multiply this in, negative e to the 3t times negative e to the t times negative e to the negative 3t, add exponents, the negatives actually are going to cancel out in front. So we're going to e to the negative 2t divided by 1 plus e to the negative t. And u2 prime is going to equal, well, negative 2e to the 2t times 0, that's going to go away. And then we're going to have negative e to the negative 3t times e to the 2t. That's going to give us negative e to the negative 2t multiplied by our g of t. So we get 1 plus e to the negative t in the denominator. All right. So that right now is our setup. So let's rewrite this just a little bit to help out with things. That's going to make life a little bit more easy when we go there. All right. If I flip and multiply this, this is going to become 1 over e to the 2t plus e to the t. Okay? And this one is going to become negative 1 over e to the 2t plus e to the t. So notice when I do multiply here, it's going to be a little bit easier when I deal with my antiderivatives for that. All right. So let's go through our setup. So the integral of our u1 prime dt is equal to the integral of 1 over e to the 2t plus e to the t dt. All right. Now this looks a little bit complicated. That's okay. It is right now, but we're going to work with this. Okay. So I'm going to focus on this one just for right now. All right. Because this is going to involve some partial fractions here in just a second. So this is why I wanted to deal with this one, because you might not have seen partial fractions in a while, so I wanted to address that. All right. And I'm going to keep these up for right now, that u1 prime, or sorry, u2 prime. I'm going to keep him up just as a reminder of what we're dealing with. All right. So it doesn't look like a way to use partial fractions at the beginning, but if we let u equal e to the t, that means du is equal to e to the t dt. Okay? Or another way of writing that is du over e to the t is equal to dt. All right? Well, when I do that, we know e to the t is already u. Okay? So, plugging that in, I'm going to get 1 over u times u squared plus 1. Sorry, u squared plus u du. Okay? All right. Well, there's an extra u in there, so I can factor that guy out. So I'm getting 1 over u squared times u plus 1 du. Now this is starting to look more like an application of partial fractions. Okay, again, what I did, just as a reminder for those that have missed it. So u is equal to e to the t is my substitution that I'm doing here. All right. And again, this u is not in any way connected with the others. Okay, I just want to make sure of that. All right. When I take the derivative of e to the t is just e to the t dt. And then I brought the e to the t over. Realizing e to the t we already said is a substitution for u. So our du, e to the t is now du over u. So that's where this piece is coming from. And then substituting in u is equal to e to the t for both of those. All right. Now I have this separated. So this is going to be my work to the side here. Okay. So WTS. All right. So what I'm doing with this, I have u squared, u plus 1. All right. When we have a repeated, sorry, not a repeated, but when we have a irreducible quadratic and linear equation, the nice thing here is there's no repeat, so this is really nice. I'm going to get a sub u plus b, or au plus b, over u squared. So anytime that you have irreducible, typically we see x here, so it would be ax plus b. So in this case, it's au plus b because u is my variable that I'm choosing to use. Plus, now our linear equation here is just going to have a c over u plus 1. Okay? Now, going through the process, I'm going to multiply all the way through by a common denominator of u squared plus times u plus 1, leaving me with a 1 on the bottom, or 1 on the top. And this is going to give me a u plus b times u plus 1 plus c times u squared. All right. Again, multiplying by that common denominator all the way through. So now I'm going to FOIL this out. All right, I'm going to get a u squared plus a plus bu plus b plus cu squared. Okay, so again, making sure I have all my terms. Au times u is u squared. Au times, oh, there it is. So there's a little bit of an error that we're going to fix right now. So I get au plus bu plus b plus cu squared. All right. Now there's a couple ways that we could have done this. If you've had this just recently, you could have plugged in values of u in order to drop some of these in order to solve for a, b, and c. But another way to do that is combine terms with the appropriate power of u. So what I'm going to do is I have a plus c times u squared plus a plus b times u plus b. All right, and now we're going to set this equal to the coefficients out on the left-hand side. Well, notice there's no u squared and no u, which means that a plus c is equal to 0. It also means a plus b is equal to 0. And it means b has to equal 1. All right. Well, if b is equal to 1, that means a has to equal negative 1. And if a is equal to negative 1, that means c has to equal positive 1. All right. So now we just plug those in. So I'm going to rewrite this just to help out a little bit. So my c is positive, so I'm just going to have that guy out in front. Minus, and we'll say plus, negative u plus 1 divided by u squared du. All right. I'm going to separate that one out to make it a little bit easier. 1 over u plus 1 minus 1 over u plus 1 over u squared du. All right, for those that are keeping track, I am going to erase this right now because I need to save room. All right, again, this is how we found A, B, and C on that. Okay, so there goes my work to the side. And now I am ready to finish this problem out. Okay, so here, this guy is just a natural log of u plus 1. We're going to talk about this value here in just a second of why I said I could do this. Okay, minus the natural log of u plus, or sorry, minus 1 over u. and technically plus c, but we do not need that integration or integrating constant there. All right. Now I'm going to plug in my values for what u was. U is equal to e to the t. So I'm going to get the natural log of e to the t plus 1. Notice I don't need absolute values for here because this is always going to be positive. Minus, well, that's the natural log of e to the t. So we'll talk about that here in just a second. Again, not equal to 0, and it's never negative, so that we're good on that one. Minus 1 over e to the t. All right, well, that natural log of e to the t, that's just t. So this becomes the natural log of e to the t plus 1 minus t minus 1 over e to the t. All right, this is our u of t. All right, sorry, u1. All right, well, we said u1 was this guy here. Well, u2 prime is just the negative version of that. So that means u2, save yourself some time, especially if you have that coincidence occur that these guys are just the negatives of each other. You can save yourself a lot of work. This is going to become positive t plus 1 over e to the t minus the natural log of e to the t plus 1. Okay, so we're almost there with this one. We've almost got it solved. All right. Just as a reminder, we said y1 of t was equal to e to the 2t, and y2 of t was equal to e to the t. All right, now we're ready to plug things into our particular equation. All right, so y of p of t is equal to u1 times e to the 2t. I'm going to have that outside of there. That's the natural log of e to the t plus 1 minus t minus 1 over e to the t. Now I'm going to put a bracket around there. Plus e to the t times the positive t plus 1 over e to the t minus the natural log of e to the t plus 1. And that is our particular equation. Now we're going to combine that again with our complementary. So our general solution is going to be of the form y of t is equal to c1 e to the 2t plus c2 e to the t plus e to the 2t times the natural log of e to the t plus 1 minus t minus e to the negative t, just to write it a little bit differently, plus e to the t times t plus e to the negative t minus the natural log of e to the t plus 1. And that is the general solution. Now, this was dealing with constant coefficients. The next example that we're going to go over is showing that we can actually deal with it with those that do not have constant coefficients in it. All right, so we're back with our third part here. I wanted to go over another example of the variation of parameters. One, because it's a really not that bad approach to for these problems, and also what happens if we don't have constant coefficients. So in this particular example, so we are going to find the general solution of t squared y double prime minus ty prime plus y is equal to t, where t is going to be greater than 0. That's our interval that we're going to be dealing with. Given the following: y sub 1 of t is equal to t, and y sub 2 is equal to t natural log of t. Now, in the book, they gave us this particular problem, and so you could actually use reduction of order in order to find this t natural log of t. So if you want some extra practice to get there, I would look back at that particular section and go over that. Okay, so what we first need to do is we are told that these are solutions of the homogeneous equation, so where this is set equal to 0. So that means they form a fundamental set. but I need to go ahead and find the Wronskian anyways because I am going to be using that in the variation of parameters. So let's go through there and just do our test. So find W sub t, so that's our Wronskian. All right, it's t times t natural log of t. So that's again the determinant of this particular matrix. So we have t up here, t natural log of t, and then we have their derivatives in the next row. So this derivative t is 1. And then we're going to have first times the derivative second. Well, the derivative natural log of t is 1 over t times t. That's going to give us 1. Plus natural log of t times the derivative of t, which is just the natural log of t. All right. So now we're going to multiply the diagonals and then subtract. So our determinant is going to be t times this is t plus t natural log of t minus this diagonal, t natural log of t. Well, notice those guys cancel each other out, so all we're left with is this is t. And we know that this is not equal to 0 because our given values of what t can be. So our Wronskian is not equal to 0, so therefore this does form a fundamental set, which means we're ready to use variation of parameters. So like before, we had u1 1 prime, u2 prime, okay, is equal to 1 over t, so 1 over the Wronskian, times, now we're going to flip these two, so this is going to be 1 plus the natural log of t, and this is going to be t in this corner, and then we make this diagonal negative, so negative 1, and negative t natural log of t. And then we're going to multiply this by 0 and our g of t. In this case, our g of t is t. So that shouldn't be too bad. All right. Well, this is going to be multiplied by 0, so that goes away. So then we're going to have 1 over t times this. So that t is going to cancel out, leaving us with just this t. All right. So that's just going to leave us negative t natural log of t on that one. And then oh, great. All right. So we're continuing this one on. I did make a mistake in the previous video, so I'm fixing that now. So I need a proper g of t. Well, g of t, we would assume is t, but this is one thing I want to make sure of, and I actually just made this mistake. So I want you guys to know from this. So I need to get this in the format of y double prime by itself. So this, if we were to write it out by itself, and I'm going to put this in red so that way it stands out. So that way we make our known our mistakes. I need to divide all the way through by t squared. So this is y double prime minus 1 over t y prime plus 1 over t squared y is equal to 1 over t. Okay, so our g of t is 1 over t, not t itself. So I want to make sure that everybody sees that. So 1 over t is our g of t. Okay, so now we can go through our calculation. All right, so this is going to be equal to, all right, this is going to be multiplied by 0, so that's going to go away. And then we have 1 over t, that's going to cancel this t out, but then we have 1 over t again. So we get the negative natural log of t over t. And then, same thing, negative 1 times 0, that's going to go away. 1 over t times t, that's 1, leaving us 1 over t. All right, so that means u1 prime is equal to the negative natural log of t over t, and u2 prime is equal to just 1 over t. Well, these are very straightforward because u1 is equal to the integral of negative natural log of t over t dt, and u2 is equal to the integral of 1 over t dt. Well, this is the natural log of t. Again, I don't have to have absolute value here because we said t is greater than 0 for that. And then for this one, this is a nice u substitution. I'm going to let u equal natural log of t, so therefore du is equal to 1 over t dt. So there's a nice cancellation out right there. So we get the integral of negative u du, which means this is going to be negative u squared. So if we continue to write that, we get negative. All right, so when we take the antiderivative of negative u, we're going to get negative u squared over 2. And then we plug in back our u, which we said was the natural log of t. So we're going to get negative 1/2 the natural log of t, the quantity squared. And down here, we have 1 over t. Well, that's easy. That is the natural log of t. And again, don't need absolute values here because t is greater than 0. All right. So, finding our particular equation, we're going to plug everything back in. So we said u1 is this negative 1/2 the natural log of t, the quantity squared, times y1, which was given, which is our t here, plus u2, which is the natural log of t, times our t natural log of t. And notice here that these guys, well, this is negative 1/2 and this is 1 in front. But they're going to be the same values. Or not the same values, but this is natural log of t squared times t. So in the end, when I simplify this, I'm going to get 1/2 t times the natural log of t, the quantity squared. So there's my particular equation. Now throwing this all together, our general equation is our complementary, which we didn't write down, but here our complementary is c1 y1, which is t, plus c2 y2, which is t natural log of t, plus 1/2 t, the natural log of t, the quantity squared. And this is our general solution. So, that's all you have to do in this. Okay?